we have seen how we can use gradient descent to train a neural network, to find all the weights and biases of a neural network that minimize the cost. However, we also saw that one of the key problems with gradient descent is that for each iteration of gradient descent, one needs to find the derivative of the cost with respect to each one of the parameters of the network, and that's extremely expensive. So one of the key innovations, one of the breakthroughs in the realm of neural networks was the creation of this algorithm called backpropagation that dramatically reduces the complexity of gradient descent, makes gradient descent a lot more efficient and tractable. So let's see how backpropagation works. So I'm going to describe this using this very simple network, but bear in mind that the arguments that I make are applicable to pretty much any network. So let's say you have two inputs, x1 and x2. That's your input layer, and you have two hidden layers, and you have two neurons in each hidden layer, and you have an output layer with two neurons as well. And we are going to focus our attention initially on one neuron in the output layer, say this one. Okay, so now let's take a look at the cost of this network for an image X. So that cost is the desired activation, we know this, minus the actual activation, which the activation being the output of layer 4 in this case. So the difference between those two, the square of that distance is the cost right here. So that's the relationship between the cost Cx and the activation or the output of this neuron number 1 in layer number 4. Okay, so what does A14 depend on? Well, A14 depends on Z14. We know that. And the relationship is established by the activation function, which in the case of a sigmoid neuron is the sigmoid function. So it's sigma of Z14. And what does Z14 depend on? Well, that depends on the activations of the previous layer through the weights and the bias of this neuron right here. So it's W114 times A13 and so on, and you have your bias B14 right here. So that's sort of the pipeline that takes you from layer 3 to layer 4, the output of layer 4, and the impact of that on the cost. Okay, so let's say we wanted to pick one parameter, and let's say that parameter is W114. We want to find the derivative of the cost with respect to W114. So the derivative of the cost with respect to W114 is equal to the derivative of the cost with respect to A14 times the derivative of A14 with respect to Z14 times the derivative of Z14 with respect to W114. This is nothing but the chain rule for derivatives, which you're all very familiar with. The chain rule applied right here. And now we're going to try and find the right substitutions for these. So there are three derivatives here, and let's look at the first two right here. This derivative, just by writing out this expression right here, you can show that to be 2 times A1 hat minus A14. And this derivative right here is going to be nothing but the derivative of the sigmoid function with respect to Z14. That's this right here. So you can plug those two into this equation, and you're left with one derivative right here, which is derivative of Z14 with respect to W114. Well, what is that? This is the relationship right here, and that's nothing but A13. So take a look at this. When you look at this, most of the terms here use nothing but the activations. The one term that does not, that is this one right here, which is the derivative of the sigmoid. So this brings us to an important property of the sigmoid, one of the advantages of using the sigmoid function. So let's take a look at the derivative of the sigmoid itself. So here is your sigmoid function. We know what that is. Sigma of z is 1 over 1 plus e to the power of minus z. And its derivative, which we'll call sigma prime of z, is e to the power of minus z divided by 1 plus e to the power of minus z squared. This can be further simplified as sigmoid of z times 1 minus the sigmoid of z. And what is the sigmoid of z? That is the activation of that neuron, A. So, sigma prime, the derivative of the sigmoid, is A times 1 minus A. The output of that neuron times 1 minus the output. So that's very convenient. Very convenient. So now we can replace sigma prime with A14 times 1 minus A14. So take a look at this now. You found the derivative of the cost with respect to this one parameter W11 without really doing finite differences, but just by computing the product of all of these activations. Many of these activations are from level 4, layer 4, and one of them from layer 3. So let's collect the ones that are, and these are all known to us, so let's collect the ones that correspond to level 4, and those are these ones right here. That's basically the first two terms up here. So that's what that is. And so we are going to take all of those, which we can very easily compute. All we need to do is look at the activations of the output layer, and we get this term right here. And that term we are going to call delta 1,4. It's the delta associated with the first neuron of level 4 or layer 4. So now we have a very simple expression for the derivative of the cost with respect to W114. Similarly, you can find the derivative with respect to W124, uses the same delta, and B14 as well. In this case, you have a 1 here. And if you can do that for this neuron, so you found the derivative of the cost with respect to the parameters, all the parameters of this neuron, and the same arguments apply to this neuron, and so you can write those as well. And so all of those have been computed without doing finite differences. Okay, so now, as long as we know the deltas for any layer, we can find the derivatives of the cost with respect to the parameters of the neurons for that layer. What's left now is how do we find the deltas for the previous layers? These layers right here. And so once again, we use the chain rule, and it turns out that you can show that if you know the deltas for a layer here in the output layer, using these deltas and the activations of the previous layer and the known weights of the current layer, we can actually find the deltas of the previous layer. Once you find that, you can use the same argument, then find the deltas for the previous layer, and so on. And therefore, the way backpropagation works is that you first go in, and take a look at the second expression here, you go in and find the delta values for all the neurons in the output layer, propagate them back to the previous layer and the previous layer and so on. So now you have all the deltas, and now using those deltas and just the activations of each layer, you can go in and find the derivatives of the cost with respect to all the weights and biases using the deltas and the activations. Very simple expressions. This is the power of the backpropagation algorithm, which allows you to compute all the derivatives that we need without going and performing the traditional approach of doing finite differences. So we can therefore compute the gradient with respect to every weight and bias using just the network activations. So now we can talk about how gradient descent works with backpropagation. This is the outline of the algorithm. As before, we are going to initialize the network with random weights and biases. That's step number one. And then for each training image, we're going to come back and look at the collection of images. But for each training image, we're going to compute the activations for the entire image. That's just feed forward. And then we're going to compute the delta for the output layer, all the deltas for the neurons in the output layer. We know how to do that. Once we're done with that, we can compute the deltas for all the previous layers. That's back propagation. Once we have all the deltas, we know how to compute the gradient of the cost with respect to all the parameters of all the neurons in the network, all the weights, and all the biases. Remember, this is still for just one image. And then you can go back and average these gradients over all the images. In our case, MNIST, you have 60,000 images. You find the average over all those images. And now you have the derivatives of the costs with respect to the weights and biases that you want. And then using those derivatives, we know how to update using gradient descent. We're going to update the weights and biases using some learning rate, eta, conservative enough learning rate. And then you essentially repeat steps 2 to 4 till the cost reduces below some acceptable level. Repeating it are really the iterations of gradient descent. So now let's take a look at complexity. You remember that we had something times 10 to the power of 13 computations needed when we used the regular approach to gradient descent to train a network. Let's see how much better we are doing here. So here the number of multiplications required to compute the cost for a single image is roughly 24,000. That's feed forward, just computing an input, pushing it all the way through to the output. Number of multiplications required to apply back propagation for a single image is this. So it's really the combination of these two, the sum, not the multiplication, that is needed to compute all the gradients corresponding to a single image for all the weights and biases. So that's roughly 48,000. And we got to average these gradients over all the images, and we have 60,000 images, so you have to take 60,000 and multiply it with this, and that gives you 2.8 times 10 to the power of 9 computations for one iteration of gradient descent, which is a 10 to the power of 4 improvement over the previous method, substantial improvement.